In the previous video, we derived Gauss quadrature using a linear approximation within the domain of our function evaluation. And as you'll recall, what we found was if I want to integrate some function f of x evaluated in the domain from -1 to 1, that we could find a reasonable approximation to this integral by evaluating our function first at -1 over the square root of 3 and again at the positive 1 over the square root of 3, multiplying our function evaluatings by weighting factors, which turned out to be just 1, and adding those two values together. And this turned out to be a reasonable approximation to our integral. I'd now like to extend this logic to 2 dimensions. Now, because we're going to be dealing with the isoparametric formulation, rather than talk about our 2-dimensional element in terms of x and y, let's discuss our 2-dimensional element in terms of s and t. And we're now trying to find some function evaluated inside the domain of a finite element that's bound by -1 and 1 in the x direction, -1 and 1 in the t direction. Recalling what we did to derive this form in 1 dimension, we're looking for locations inside this square where we can, evaluating the function at these values, and it will turn out there will be 4 of these values, that evaluating our function at those 4 locations and multiplying them by some weighting factor will come up with a reasonable approximation to the function, the integral that we're trying to solve for. Remember what we're doing here. If I'm going to try to visualize this 2-dimensional space and a function that might be evaluated or be thought of as coming out in a 3rd dimension, what I'm saying is that if I have my 2-dimensional domain, and there might be, I could visualize some function which I might visualize as a 3rd dimension above my 2-dimensional planar domain. I can now say that think of the integral I'm trying to solve is the area or the volume encompassed by this 3-dimensional shape. So what I'm looking for is locations inside my plane where evaluating my function at these locations, doing so, multiplying by this area of my plane gives me a reasonable approximation to this volume. So it turns out that the 4 locations I'm looking for are equally spaced from the origin, which might not surprise you. I've labeled them, so I have an S1 location and an S2 location, and I have a T1 location and a T2 location. So what we're looking for now is a reasonable approximation to a function f, a function of s and t, inside the domain or the area, integrating over the area ds dt from -1 to 1, from -1 to 1. And I'm saying that we can come up with a reasonable approximation for this by multiplying the 2 weighting functions, one weighting function that corresponds to my s values and another one that corresponds to my t values, and evaluating the function at these 4 locations and then summing up the 4 evaluations. So all that is left is to find out what this W1 and W2s are and what this S1, T1, S2, and T2 are. It should not surprise you, because we're just extending what we've done in 1 dimensions, that these values also turn out to be negative 1 over the square root of 3, and positive 1 over the square root of 3. And again, our weighting values simply both turn out to be the value 1. So as a result, our formulation to evaluate this integral in two-dimensional space simply turns out to be to evaluate the function 4 times, sum up these evaluations together, and the evaluating both at negative 1 over the square root of 3, negative 1 over the square root of 3, positive 1 over the square root of 3, positive 1 over the square root of 3, and the two inner combinations. In our next video, I'll discuss how to apply this formulation to the isoperimetric formulation that we derived in the previous lecture.